This is a reason.
Okay. Yes, oh, thank you very much. Yes, thanks for the introduction. So today, my name is Xiaobao, and today I would like to share with my knowledge on the 3D puzzle-inspired metamaterials with the dual Poisson's ratio. So as we all know, the mechanical metamaterials receive the increasing interest from the scientists and researchers because it has unusual mechanical material properties like the negative stiffness ratios or the negative Poisson's ratio materials. So today I will just focus on the Poisson's ratio problems. So regarding the fundamental equations about the Poisson's ratios, it could be the positive or it could be the negative. And the range of the Poisson's ratios of isotropic materials could be from -1 to the 0.5. So a lot of researchers and scientists developed a lot of families of negative Poisson's ratios materials in 2-dimensional or 3-dimensionals. So in the 2-dimensional, it could be the honeycombs, it could be the rotational squares, and also it could be like the composites that I developed before, and it could also be like the 3-dimensionals, like the forms, lattice, and chiral structures. So, however, I would like to ask some questions. Is it possible that some materials with dual Poisson's ratio and quasi-static conditions and I mean that the same loading conditions, is it possible to have two different Poisson's ratios? Then here I would like to share what I found. So the motivations. I was inspired by the most famous figures from the MC Escher, the water flow. I was like interested about this solid, and actually this solid has a specific mathematical names. It's called the first stellation of Robic dodecahedrons, and also we can just say it's easily because it's so famous. It's called like Escher solid. So it has a lot of that's unique features in the mathematical ways. But for me, I would like to divide these solids into 6 identical building blocks. And each building blocks will be built by the identical pyramids. How I do it? Here is my designs. So I started from the simple geometries, the pyramids, and I only use the principles about the symmetry. So I repeated to build these simple geometries by choosing the symmetrical planes. And after repeating 4 times, I get my first designs of my building blocks. And if I repeating more, I can get like design 2 and design 3. I call it like my families about these mechanical metamaterials. And then I need to assemble these building blocks. And I also use like the symmetrical principles. So I repeat these building blocks by YZ planes, XY planes, and XZ planes. This is my initial designs about these mechanical metamaterials. And by understanding about the load transmission mechanisms about these geometries from the contact mechanics and strain energy method, I optimize my designs and build my numerical simulation models. In Abacus, this is my families, this is the numerical models, and I simulate my models in the Abacus, and I use the periodical boundary conditions applied on these unit cells. And the coefficient of the frictions was set at 0.1 in all my simulations. So previous is the simulation, and here I would like to use the multi-material 3D printer, the Objet ADAM 500. It's used the polyjet technologies, so it have like higher resolutions. I choose the materials very gray. It's original materials. I tested these materials and get the material properties from the S-team standards, and here on the right figures it shows the experimental curves and also the finite element simulation curves. And I use the power law plasticity models with the damage evolution law to curve fitting my experimental curves. And on the lower lines of my slides is the material properties I inputted into the simulations to get these simulation curves. And I would like to use these material properties for my future simulations. So here, originally I would like to show you the videos, and I will try again if it is possible. Looks like not, but I mean that during the videos, I mean that I'm pulling out about my examples into for these two building blocks, and it will show that the negative Poisson's ratios, and you will see the materials will expand isotropically in the z directions and the x directions. And if I choosing the different building blocks under the loadings in the same loading directions in axial tensions, it will be shows almost zero positive Poisson's ratios, and the stress strain curves, the strength and the stiffness almost like 10 times, 40 times higher than the negative Poisson's ratios effect. So, yes. So here is the deformation history of this auxetic effect. On the left figures, what I would like to show you is my experimental result and the simulation result. What you can see here, the simulation result could capture the experiment curves, and my analytical models based on the contact mechanics can predict the stiffness about these mechanical metamaterials. And also the Poisson's ratios, what you can see here, the result of the simulation and the experiments, they are quite similar. And the analytical models almost predict the Poisson's ratios reach the limit of the isotropic materials. And if we look at the details of the numerical simulations, it gives us the physics insight, because the local deformations of these building blocks is very small, but the global deformation is large. And if we're looking at the interlocking eigenset cases, what you can see here, the simulation results also can predict the experimental curves pretty very well. And no matter the stress strain curves or the Poisson's ratios diagrams. And the numerical results also give us the physics insights that the strains is localized in the building blocks, and the global deformation, however, in this case is very small. So this is like the two cases. And then if we understand the two cases from the analytical models, from the numerical models, from the experimental results, then we have the confidence to move further regarding the families. So here is my families, design 1, design 2, and design 3. In the negative Poisson's ratios cases, what you can see here, the stress strain curves, the Poisson's ratio diagrams, they have the similar trend, right? They have almost the similar trend. And if we change to the zero Poisson's ratio cases, or it's called like the interlocking cases, it also shows the very similar cases. All the Poisson's ratios is close to zeros. So this is like the families, how the families behaviors. Then we would like to see if we just to combine these like each cells into multiple cells, what it behave. So here what I would like to use the 3 by 3 by 3 cells as examples to illustrate the mechanical behaviors. And whatever here I was interlocked, just to change the loading component building blocks in C232. Here the notations about C is the name of each cells, and the 232 means under these coordinate systems what's the unit cells. And on the right figures, what you can see here, in the middle figures, it shows my analytical models and the simulation results consider about the deformations, the strains of each unit cells under the front layers of z directions. What you can see here, the analytical models works pretty accurate. And on the right figures, it gives the analytical result and the simulation result in the middle layers about z directions. And also what you can see here, the analytical models works pretty very well. And since the last layers is the symmetric of the first layer, so that's why I didn't raise it here. And the reason why it's accurate because here I give like some assumptions based on the observation on the physics. I just said like I give the assumptions like the deformation of unit cells is independent, and it should be like isotropic in each directions. So at least in the elastic regions, it works very well. So that's tell me that this kind of mechanical metamaterials, we not only can predict the unit cells, but also if we combine into the multi cells, every material point in these mechanical materials, the mechanical behavior is predictable. So that gives me like the sense to build a mechanical binary coding box. As we all know, like the coding box normally is electronic, and here I would just like to illustrate my ideas with these 3x3 multi-cell structures. So the lower button, the lower row, the last rows, the fourth last rows, is the case what we faced before. And the first 3 rows is I changed the interlocking component into the different locations. And what you can see, if we observe on the morphology change, the shape configuration change in the XY plane and YZ planes, and you will see some horizontal bars of each unit cells, they will not change the relative positions between each others, but others will be changed a lot. So that means if they are connected to each other, I was thinking this is like a coding tells is 1, and the separate connections is zeros. So for example, at the first cases, the XY or YZ planes, they show the different, the coding, the shape morphologies. And this is like my codings for the XY plane and YZ planes. And here I change the locations about the interlocking part. It will also change like the XY and YZ shape morphologies. And even, if, for example, the YZ planes, they keep as the same, like the third rows and the fourth rows, the YZ plane, they are the same, but XY planes, it will be coded. That if you code it, that means XY plane, they will choose the different shape configurations. So this is very good because that means we can use very less unit cells to contribute very large coding space. So this is like my results about number of combinations about these unit cells in the 3 dimensionals. And here the maximum, the unit cells I only use 8 by 8 by 8, but the increase is the exponentially. Here is like the logarithm, the axis. So that's like a very good, result, and it's very interesting because if we can also detect the force, because I think it's possible. Everything is predictable. That means we can also observe the load displacement. To check if XY plane, YZ plane, they behave the same morphologies, the load displacement will also show some difference. So that's like a very, that's a security box you can code in your banks or whatever it's for the security purpose, like a computer. So this is my conclusion and it's my ongoing works. So today I will just raise the questions to ask the fundamental equations about the Poisson's ratios. Means that for 100 years ago, Poisson derived these equations, and today I would just like to raise the questions. Is it possible in some cases these equations is not valid anymore? So I use these mechanical metamaterials to prove that actually in some cases, under the definition about the Poisson ratio equations and the same loading for the static stators, they will have like the dual Poisson ratios. So by understanding these fundamental physics in these morphologies, and also the load transmission mechanisms, the sleep and interlocking derivation I didn't show you here. But from analytical models, it shows that this is the key for the microstructure mechanical models. And what we are doing, the ongoing work is finally, we are finalized this paper, and then we will just prepare the experiment for the multi-cells, because it's more complicated to do the test. At least I needed to make sure that the XY plane movement should be free when under the loadings in the third directions. So that's like pretty all my works. Thanks.
Thank you.